Hello everyone. In this video I'm going to discuss complex numbers, especially with the perspective of control systems. So let's start with the simple transfer function, which looks like this. G of s is equal to s squared plus 2. Okay, so if you know the basics of control systems, you would also know that the roots of are called poles, right? So the poles mainly define if the system is stable or not, and they show us a lot of other properties which are required for the system. So if I take this equation, let's say it is equal to, this is n of s for the numerator and d for the denominator. I would say d of s is my denominator, so you can see that it is a quadratic equation and it will have two solutions or two roots, or within controls perspective it will have two poles, right? So what will be the two poles? If you solve it, you will see that you will have to use the quadratic equation, and you will have poles at s equal to 1 plus j, and I call it s1, and the another pole would be s at minus j. Now if I want to plot these poles, I have this very common plane over here. It's you can call it a complex plane. In complex plane we have the real part, the real axis, and we have the imaginary axis. And if I want to plot this, how I can do that? Let's say I mark these locations 1, 2, minus 1 and minus 2. This is plus j, this is minus j. So if I want to plot this thing s1, it will be like this. And here at this spot I have s1, which is equal to 1 plus j, and over here at this spot I would have s2, which is equal to s minus j. So very easy and very common plane for all of us, right? We are very much familiar that how we plot the complex numbers like this. Let's say I want to present the complex numbers in a different way. What could be that method? That method is called Euler's representation, right? Or you can just call it that a way to represent the complex numbers using Euler's equation. So what is the Euler's equation? In case you don't know, it looks like this. We have E iota theta is equal to sine theta plus iota cos theta. So it's very interesting that how this thing can represent a complex number. So rest of our discussion would be on that part. So how we can represent this complex number s1 and S2, right? So just look at this. We have S1 as a complex number, and I would say that I can present it as A E iota theta. What is this? This is a complex number. This is the magnitude of the complex number. And what is this? It is the phasor. So this is the information of the phasor, and this is the information of the magnitude. So how this phasor and this magnitude will represent a complex number? Let's see how we can do that. And for now, just keep this part in your memory, like what is A and what is E raised to the power iota theta. So what I'm doing here, I'm picking up another plane. Okay, I don't know what is the name of this plane, just it's an empty plane, and I have this point over here. I have this point over here. Let's call this point S1, which you remember is a complex number. So how can I represent this point, this S1, this S1 point? So let's do this. If I draw a vector from this point to this point, right, which is required, from the center to the pole, which is required, and if I know what is this theta, and if I know what is the magnitude, right, so can I know what is the location of this thing, this point? So location of, okay, S1. So we are going to do that. With the knowledge of magnitude and the phasor, we can now locate any point in this plane, right? Let's say if it is here, we can just do this, right? If this point is here, we can do this, right? If this point is here, we can do this. So the point is, with this vector and with this angle, right, wherever you want to do, like from this perspective up to this point and up to this point and up to this point, right, the angles, different angles we have, and with the magnitude of vector we can trace the location of these points. So that's the other method. So let's have a look on this same plane again. We have it in here like this. Let's say we have this part as cosine and this part as sine theta, and we have a point that we want to locate that's given at here. Let's say I have a vector, it's called iota theta, e raised to power iota theta. This is not very intuitive, I know, but this the roots of this concept go a lot deeper into the mathematics and the abstract concepts, so let's not go into that and just stick with how can we track the location of this blue point over here. using these resources. So what are the resources? E iota theta, sine theta, and cosine theta. If we have these things in hand, can we trace the location of this blue point over here? So we are trying to do that. Let's say I will do this and do this. Now the magnitude of this thing will be equal to sine square theta plus cosine square theta. Okay, it's a trigonometric identity that sine square theta plus cosine square theta is equal to 1. So E iota theta squared is equal to 1, or if you just remove the square, it will be simply equal to E iota theta equal to 1. So what does this mean? The magnitude, right, the magnitude of this thing is equal to 1. So if you have this thing and it is enclosed in a unit circle, let's call it unit circle, then on this unit circle any point can be tracked using only theta, right? So this thing becomes the phasor. Okay, this thing, if you know the angle of theta, you can track any point, the location of any point on this unit circle, because we know that its magnitude will be 1. So what if we have a magnitude that is greater than 1 or less than 1? We can also do that. So what we have for magnitudes which are greater than or lesser than 1, like this, like this, we have this can be tracked with iota theta, we know that. This can be tracked with e iota theta, we know that. But if we want to increase or decrease the magnitude, we just put a in front of it, right? We multiply with a. So these points, right, their true location will be traced by a iota theta, where your a represents how long is this vector, and this thing represents what is this phasor, and together they will be generating a complex number, right? So are we really sure? To prove that this is a complex number, or this will be generating the similar complex number that we saw over here, like this, let's try to find out the magnitude of this thing and phase of this thing, and then put it in the Euler's formula over here, Euler's equations, and then see what number do we get. So we had a pole S1, let's say we just take this one, and it was equal to S 1 is equal to 1 plus j. If I take magnitude of this, it will be equal to, you know how to take the magnitudes. We take the real part squared plus the imaginary part squared, right? We don't take any iota or j or whatever you call it, right? We just take the coefficient. So coefficient of j is 1, so it's 1, and this will be equal to underscore 2 or 1.414. If I take the angle of S1, this will be imaginary upon real. So sorry, it's a tangent inverse, so both are 1 and 1, and tangent inverse 1 is equal to 45 degrees. Or 0.8 radians, right? So we have got this. Now if we put the same values in here, you will be getting the same complex numbers. Let's say we had the I say it's underscore 2 iota, and this accepts in the radians, so this is 0.78, and when you solve it, you'll see that it is equal to 1 plus j. Right? And similarly, if you remember S2, so S2 can be found like this, right? And when you put it in here, this will be minus 0.78, this will be 1 minus j. So this is similar formula. Previously here was plus. If the iota is in minus, then we have this, right? So this is just for the information. So what's the point? The point is, if you know the magnitude, the phase, you can always get back the same complex numbers. So now we know S1, which was equal to 1 plus j, is actually equal to underscore 2 e raised to power iota 0.78. Okay. So this thing, although this looks quite different with the e and all the things in it, but it's actually equal to this part. Now in control engineering, which form of complex numbers is used? It actually depends. Mostly in control engineering, it's just this form. Right, the real part and the imaginary part. But sometimes representing a complex number with a raised to the power e iota theta can serve a more useful purpose, right? So it depends on the application. One application that comes into my mind is the Nyquist plot. So when you're trying to understand the Nyquist plot, and if you go into the concepts, you will see that when we are defining that we have to sweep the frequencies from 0 to infinity, then understanding how the system or the Nyquist plot will behave at the infinity, this form of representation, a complex number representation, serves a very good purpose, right? Because in the magnitude is straight away shown with the help of a, right? And when this is infinity, a lot of things start to make sense and become intuitive. While in here, finding out the magnitude is a bit difficult, right? So you have to get into the process of finding out the magnitude, and this might become less intuitive. So it just depends on which form you want to use. We don't have to confuse with this representation. So whenever we see this type of number, right, we can immediately say that okay, this is also a complex number, and it can easily be converted into this form, or this form can be converted into this form. Here we have a little animation in which we can see that we have a unit circle and a point that is rotating on the unit circle in a clockwise and anti-clockwise fashion. So if we just do a single rotation, you can see that we have a sine wave and a cosine wave. And if we progress in time, that unit circle can be thought of like a helix. A helix, as you can see in the little animation on the top. So we still have a dot in the plane, but that progresses in the time, and it rotates as well. So you can see that you still have the sine and cosine waves that are progressing in the time.